What's going on YouTube? This is Ipsec. We're doing Ellingson from HackTheBox, which was a really fun box themed after the movie Hackers. The initial page on this box is coded in Python Flask with debug mode enabled. So that means when you cause the page to error, it's going to output a big stack trace. Additionally, pin code validation is disabled, so if you just click the little terminal icon, you can run Python code directly on the box. I know this sounds super silly, but it's actually affected some major companies. For instance, this is how Patreon had got hacked back in like 2015. So you run code on the box and you'll notice you can't do any reverse shells because there's some type of firewall that's preventing you. You can, however, drop an SSH key, then SSH into the box. From there, you'll find you have to escalate to a different user. You do that through cracking hashes, but there is a SetUID binary that is a ROP challenge. And this part can be really difficult if you don't have any experience doing like buffer overflow type exploits. But if you do, then this is probably going to be super simple. I have a video called Bitterman that walks through this exploit in particular. So if you have questions, I'd refer you back to that video. All that being said, let's just jump in and do this box. As always, we start off with the nmap, so -sc for default scripts, sv enumerate versions, oa output all formats, put in the nmap directory and call it Ellingson, and then the IP address, which is 10.10.10.139. Can take some time to run, so I've already ran it. Looking at the results, we have two ports open. The first thing we have is SSH on port 22. Its banner is telling us that it's a Ubuntu server. We also have HTTP on port 80. And its banner is telling us that it's Nginx, also running on Ubuntu. We had the nmap script http-title run and tell us the web page title is Ellingson Mineral Corp. Nothing too interesting, so let's just hop over to the web page. Going to Firefox and browsing to it, we get what looks like a standard company page, potentially some blog post here. Going down, we have a Meet the Team page of Hal, Margo, Eugene, and Duke. All characters from the movie Hackers. And it's now giving us some information, so I'm trying to think what I can use this information for, and potentially usernames. Once we figure out the username convention schema, is it first initial, last name, last name, who knows. But if it's first initial, last name, then we have three potential usernames, M. Wallace, E. Belford, and D. Ellingson. So just keeping that in the back of my mind as we go through this box. And then some potentially more blog post. I'm going to press Ctrl-U to see if I see what this page is built with. Looking for hints that's like using WordPress, Joomla, E104, just something that would build a web page automatically that helps us search for it. We have what looks like to be a Easter egg here of just a line from Hackers, but nothing in the source code tells us that it's built with anything, so we don't know that. Let's just go back to the web page and then click on a blog post. We have this page that says a virus was planted. If we go to articles 2, which is probably the next blog post, we have something telling us that there may be some type of denial of service protection in place. If you attempt to log into a service more than 5 times in 1 minute, you'll have your access blocked for 5 minutes. So probably won't do any type of username brute forcing on this box. The next thing we have on Article 3, suspicious network activity. It's telling us that we should change our password, and the most common passwords involve love, secret, sex, and God, and that's coming from The Plague, which if you've seen the movie, you know that is going to be Eugene Belford's character, but if you don't know it, just keep moving on. Keep this in the back of your mind. It will help you when it comes to cracking something later on. You don't need it, but it does help. So the next thing I do is check Article 4, and we get a weird index error. This page is telling us that number 1, it's a Python Flask application, and number 2, it's in debug mode, not production mode. So in old versions of Werkzeug, I think that's how you pronounce it, it didn't have any protection on opening an interactive terminal to debug the application. This was exploited in Patreon, I believe. If we do Patreon debug exploit, how Patreon got hacked, publicly exposed Werkzeug debugger. So that's what this exploit's going to be. I think in version 0.11, it got patched to involve a debugger pin. But essentially, we can just run Python commands straight on the server. So if we do print test, and I'm doing the Python 3 print because we see Python 3 here, you can see it. So if you want to see what it looks like now, I have a demo application. We've just opened up in Vim. It's just using this, setting it in debug mode and hosting a page. So if we do python demo.py and then go to localhost 5000, we get the page. Let's put some bad code in here so we get a crash. So if we do x is equal to int please subscribe, this code should crash because it's horrible code, mainly because I wrote it, but it does crash. And then we see the same exact icon here. So if we open this in a Python shell, it's asking us to enter the PIN. And if you look here, we have the debugger PIN. So this is a small protection built into this. I don't know if you can brute force that if it has a timeout or things like that, but that's a protection built into this page now. But old versions do not have that, and you can just run code straight on it. So since we can run code, we should probably try to get a reverse shell. To do that, I'm going to import the getOutput module from subprocess. So from subprocess import getOutput. And what this is going to do is just let us run commands. So if we do getOutput who am I, we can see with the user HAL. We could do ping. Let's see. What is ping? Is it ping-c or -n for Linux? Localhost. Probably -c. There we go. I always get that argument mixed up between Windows and Linux. So ping-c1 and then 10.10.14.3 to see if it can get back to us. We don't have any output yet. We'll try a different command. Let's just see if we hung the web server first, since I ran a command and... Okay, there we go, we got output. Let me try this real quick. Get output ping, and then print test. Okay, so we don't hang this web server if we do 10.10.10.139. You can. One of the dangerous things about playing with things like this is if you do a long-running command and it's not threaded, you could just hang the whole web server. So always be conscious of that. Whenever we try to ping, we're getting a operation not permitted, and that ping doesn't make it back to us. We can also try, do we have curl in this box? We do. We can do curl 10.10.14.3, and then in our box, say nclvnp 80. Curl is going to default to port 80, and it does not get back to us. So there's some type of firewall rule that's preventing the box from getting out. So in that case, we should do get output, and let's check if we have SSH keys. Since we have code execution as HAL, we should be able to drop an SSH key and gain access to it. This output is a little ugly. I'd like to have this formatted a bit better because of all these like /n's not treating as a new line. So what I'm going to do is I'm going to create a new command. I'm going to type it here because it's just easier to read. I'm going to define run cmd, and then I'm going to do from subprocess import get output. Then I'll do x is equal to get output cmd, and we'll do print x, and then end is equal to new line character. So all these new lines have /n. So all I'm doing is saying, hey, print this out, and on this is the new line. I don't know if I actually need that because that may be the default. We'll try it with both. So copy this, paste. Now I have this command called run. We do lsla on home. Print's nice. Let's get rid of this end because that is the default. So maybe if we just did print on this, it would work. Paste this. Run. So yeah, we don't need that end thing. But now we have a bit better terminal. So we can look in this, then /.ssh, and we have read-write access to authorized keys, read access to IDRSA, and then the pub. So the first thing I want to do is steal this private key. So let's do run cat IDRSA and specify the full path. And then we can grab this. And then v ssh.hal.encrypted, because I noticed when I was copying it, we had this proc type for encrypted. And I'm not going to try cracking this, because if we go to the ipsec.rocks page, you can just do crack SSH. And in this one, we do that whole process. It's actually a rabbit hole, won't crack. So that's why I'm not going to bother with it. And if I was doing this box for the very first time, I definitely have that running in the background, just because if it cracks, who knows, it may be a password reused somewhere. But since that's not going to crack and we have read-write access to authorized keys, I'm just going to do ssh-keygen-f HAL to generate a SSH key for the HAL user. If we cat hal.pub, there's going to be the public SSH key that lets us log in. So I'm going to grab this, and then again, because it's just easier to read here, I'm going to run, and then we'll do echo, paste the key into star.ssh authorized _ keys, and that. Okay, so we can copy this whole thing, go into Firefox, and then paste this in. Let's see. I made a mistake here. We don't want that single quote because I closed out the single quote here. So I just got rid of the one single quote. Paste it. There we go. Now we can do chmod 600 on HAL, the private key. And if we ssh-i that key, HAL at 10.10.10.139, it does not work. If we do -v, we'll see that it denied our public key and then moves on to going through a password. So let's go back here, hit up a few times to cat this file, cat ssh authorized keys, and we see something weird. This file did not end with a line break, so it looks like we may have just appended straight to it. So I'm just going to run our command one last time, run this again. If we cat authorized keys, this is beginning on a new line now, and let's try getting in. I should have took verbose off, but we get in. So now that I'm in here, the very first thing I want to do is clean up what I potentially broke. So let's go into the authorized key file, and we can see this SSH RSA starting in the middle of this. So let's just do $$ to delete everything after the cursor to clean up that key, and then hit W to write this. So now this one key is going to work still. If we didn't do that, and that key actually was in use and someone went to use it, it wouldn't work, and they may check this file out and notice something fishy. So always make sure you fix what you screw up. So now that we're on this, we can do lsla. We don't have anything. There's no history file, no nothing. So I want to run LinEnum. So let's open a new pane. Let's just cat /opt LinEnum, linenum.sh, base64-w0, and then we'll do xclip -selection primary to put in our clipboard, and then just let's go to dev shm v linenum.b64, wrong clipboard, there we go, base64-d linenum to linenum.sh. So now we should have this file on it. And the reason why I'm doing this is because the previous attempt when we tried to do reverse shells, it didn't work. So we can check if that rule was on the web server or on users. So if we just curl 10.10.14.3, still can't get to it. So that's why I dropped LinEnum to the disk. So if we run this now, thorough tester enabled, that's fine. We can clean this up, and then just let the script run and we'll go over the output once it's done. Now that LinEnum is done, let's go to the top and see what it found. The first thing it finds is kernel information, which tells us the kernel was compiled on February 6th. Not too interesting since this was compiled around the time the box was released. If it was a much older kernel, I'd look for kernel exploits, but any kernel exploit that gets released probably came out after the time this box was made, which makes it an unintended path that I don't really care that much about. We have information about Ubuntu, not interesting for the same reasons. The host name is Ellingson, not too interesting. This current user/group info, we see we're a member of the ADM group, which that is definitely interesting. ADM users have generally better access to overviewing log data. So I'm just going to create a pane to my right, and we're going to take notes here. So we can put member of ADM, and then let's see, we got to go back to where we were. Let's just search back, and here we go. So the users that have logged onto the system, we have the Plague logging in around May 7th, HAL October 14th, and Margo October 14th as well. Nothing too interesting there. There are 4 users, I believe. At least on the web page, there were 4 users, and we only see 3 here, so one of them has never logged into the box. If this was an actual engagement, maybe I'd try default passwords against that user. Try like password123, but you also got to keep in mind that there is that fail to ban protection that is indicated on the web page. If you fail to log in like 5 times, I think your IP gets banned for 5 minutes. So that's why we're not worrying about that. Let's see, group memberships. This page isn't too interesting. Let's go to the next. Admin users. This is telling us that the Plague is an admin and we are an admin. We're a member of the ADM group. The Plague is a member of a bunch more, ADM, sudo, LXD, etc. Contents of etc passwd. This is going to show us that one extra account. It looks like Duke is the one that hasn't logged in, so that's the one I tried default passwords with. Super user accounts, root, permissions on home directories. It doesn't look like we can get into anyone else's home directory. They're owned by the user and their group. And looking at this, user and group are RWX, and everyone else is nothing. So files owned by our user. Nothing too interesting here, just all the default files in home, and then some LXCFS, which may have been more interesting if we were a member of the LXC group. Hidden files, we can skip that. Word readable, home directories. SSH keys, we already have those. Environment information. Path, shells, UMask. Cron jobs all look like they're standard, nothing unique. Cron tab, standard, nothing unique. Systemd timers, looking over here at the units. Everything looks standard. IP address, we see we're in the box that we SSH to, which is 10.10.10.139, so we're not in any container. ERP history, nothing. DNS stuff. TCP. We see that there's an additional thing. Port 8888 is listening, so that is going to be interesting. So what is port 8888? And I'm going to guess this is going to be the Python web server. And then port 80 is Nginx, that's acting as a reverse proxy to this Python web server. So we want to see what user this is running as. Since we can see the PID, I'm guessing it's running as us. And since our code execution came back as us, it's most likely going to be running as us. etcinitd, systemd, there's just so much information here. HT passwd found. I'm going to guess these are like default creds or something. I don't know exactly what this is, but I see like Python failed to ban test, so I'm guessing these are just test credentials. File locations, compilers, sensitive files, can't really read any. SetUID files, I see one that is really interesting. We have garbage, and that is March 9th, 2019. So this may be a good box to just go look at everything that's happened on March 9th, because I've seen that date a few times, so that's probably when the box was created. And we can see what else the creator did on that day. But everything else in this SetUID binary looks standard, and then set GUID, it's probably going to be the standard stuff. And there's only so much of LinEnum output I can go through, so I'm probably going to skip the rest of this and just begin looking at what we have. So if we do netstat-alnp grep 4888, we're going to look at what this Python program is listening on that port. So if we do a ps-ef grep 1186, we can see the Python program is opt-corp-web run.py. So let's see if there's any credentials in this web server. So there's run.py and run.sh. I'm guessing run.sh will start run.py, so we can start with that. And we see that Flask debug is set to 1, and the pin is set to off. And then it executes this Python script. So that's putting this in debug mode, and then also telling it to ignore the pin. So that's where the vulnerability comes in. Run.py, we can see it's a Flask application. Doesn't look like a database. Everything is hard-coded. We got a few JPEGs. I don't see any passwords. We could grep this entire directory for password to see if anything comes back, but it's just the templates. So nothing too interesting in this. If you want to see the Nginx configuration, we probably can pull that. It's probably under sites available, cat default. And then let's see. So at /index, it's doing a proxy pass to localhost 8888. So this is how it's serving this web page. So it is just acting as a reverse proxy. So we answered what is port 8888. We got this SetUID binary, so let's go take a look at that. If we execute user bin garbage, we're going to get user is not authorized. This attempt has been logged. If we do strace user bin garbage, we can see, let's see, it doing a call to get UID right here, coming back as 1001. If we grep passwd with our username, which is HAL, we'll see that we are ID 1001. And then it exits. And I don't see it, actually right here may be doing some type of log. So maybe it is actually logging. Not positive, but let's just take this binary and put it on our local box and analyze it with Ghidra. So scp-i HAL 10.10.10 139 user bin garbage, put it there. We forgot to specify the username. And then let's open up Ghidra. And let's see, we need a new project, non-shared, Ellingson garbage, SetUID. Let's make dir garbage. Okay. Open this, which is going to be the disassembler/decompiler. File, open. Oh no, we want file, import, and then import this binary. Yep, it is in a 64-bit ELF. Let's analyze it. Select all. And I'm just going to wait for this little bar at the bottom right to finish doing all the analysis. Shouldn't take too long. There we go. It's done. And let's look at main. Where is main? There it is. Hit too many keys. And then we can go to the call graph to start out and kind of analyze this. And we see a call to check user. So looking at check user, we can see it's going to do that get UID call. And then we got a few jumps down here and then an exit. And then right here, it looks like user is cleared for access to the program. So if get UID and then goes down this if train, let's just get out of the call graph because it's easier to read it this way, I believe, especially when you have decompiler output. So we have an if statement that has three things. If var1, and var1 is going to be the output of getUID, is not equal to 0x3a, and I believe that is 102. So if we do Python print 0x3a ea, it is 1002. So if var1 is not equal to 1002, 0, or 1000, print the user is not authorized to access this application. Otherwise, user is clear to access the application and continue. So since we are UID 1001, we're not clear to access this application. And then looking at main, let's go back. There's nothing that really happens before this check user call. So we don't really have an attack surface. So I'm going to ignore this binary for now. We probably should look at who is 1002, because we see 1000, 1002, and 0 can run this. So let's grep 1002, etc passwd, that is Margo, and then 1000, that is the plague. So those are the two users we probably want to target. We want to get on either Margo or the plague because we can access that binary. If we get on the plague, he's also a member of sudo, so there'll be something really good there. So let's save this for later. And then we're a member of the ADM group. So we can see what files we can that group provides access to with find/-group ADM. I do -ls so I can see all the permissions, and then to dev null to hide errors. Maybe group should be lowercase ADM, and now we're getting the output. So we can see the very first file we have is var backups shadow.back. It was modified March 9th. We have a bunch of log files and then stuff in snap, which I believe is a package manager for Ubuntu. So this file is definitely interesting. The first thing I want to look at is the date on this file and the one in etc shadow. So we can see that etc shadow, the group is shadow.back, it's ADM. The important thing, though, is our backup's 1309 and etc shadow is 1330. So ours is slightly different, so that means there's going to be different different entries in it. I think we can do -- is it time-style is equal to full ISO. There we go. And we can actually get the dates or the timestamp. So we see the backup was created at around 8:42 p.m. and then etc shadow, the last time it was changed was around 10:21. So there's about a 90-minute window which a user could change their password and us not see it. So what I'm going to go to do is go into var log, and I'm going to grep passwd on auth.log. And this will show us all the password changes. So we have, let's go back here, create kind of a pseudo timeline. So at 2042, we have shadow backup that we have access to, and at what is etc shadow 2221, we have shadow latest shadow. So March 9th, 1920, we have HAL changing the password, and then Margo changing the password, and 1921. Duke changes their password. They've never logged into the system. That's weird. So maybe that's when this account was created or something. But the next thing we have is down here, 2206. The plague changes. And then we also have HAL changing. And 2207 is Duke. So, HAL, Duke. Now the thing that doesn't match this timeline is Margo. Margo's 1920, and she has not changed her password since we have this backup. So chances are the shadow backup will contain a valid password for Margo. So let's go cat that shadow backup. So var backups shadow.back. And I'm going to grep -v because I don't want anything with that star. So we can do like that. And now we'll only have the hashes, and they're all $6, which I believe is SHA-512 crypt. So we only want to grab the first two. So I can do awk -F, a field separator, print 1:2. And now we have stuff we can crack. If we're concerned about time, I'd only throw Margo in, because Margo is the only one that I'm assuming has a valid password, but it's still useful knowing users' previous passwords in case they use like the date, a season, or things like that. So I'm going to go ahead and crack them all. SSH to my Kraken, and this is just a dedicated box for cracking. I just recommend not doing cracking in a VM because VMs are slow and cracking is very intensive. So let's go into hashes. We can call this file Ellingson, paste it, and now I'm going to do /hashcat, example hashes, pipe it to less, and I want to see $6. So the example format here, that's SHA-512 crypt, and the mode is 1800. So /hashcat -m 1800. I'm going to do a $O for optimized kernels. This means that if the password is extremely long, I won't crack it, but if the password is of, I guess, a normal length, it will be a bit quicker. Then I'm also going to specify --username. And what this is going to do is take that hash dump format into username:#. So when I go to output the hashes, I can see exactly what I cracked. And then we want the hash file, which is going to be hashes Ellingson. And then the word list, we'll do opt word list rocku.txt. Let this crack. It's going to initialize all the OpenCL runtimes and then begin cracking. We can hit S for status to see the time, and we've already cracked one. It's only going to take 2 minutes. So let's grab, actually let's not grab that password. Let's show you what that --username does. So let's open another SSH session, cd hashcat. We can do /hashcat -username -show -m 1800, and all we have to do is specify the hashes file, so hashes Ellingson, and this will tell us not only the hash and password, but we keep the username. So we can see the plague has a password of password123. We could try this. Keep in mind, we're going to set off a log, and we don't think this is going to work because he set his password after the backup, but we test it out anyways, because why not? And we get auth failure. So that's not his password. We get a second crack, I am God S08 or $08. Running this show again, we can see that is going to be Margo's password. So let's grab this. And we can do su-margo and go in. And keep in mind, we just created a log alert of HAL suing to the Margo user. Why would we do that when we have SSH open? So the better way probably would be SSH, and this is just going to maybe not flip off as many alerts because maybe HAL never SUs to different users. So now we're in as Margo. We can wc-c on user.text. See that's MD5 something a line break to get to 33 characters. We also can run that garbage binary, and it asks us for a password. We could do strace potentially and see if the password comes out. If we want to look for like a compare or something. Let's see, I don't really see it. So what I'm going to do is just go back into Ghidra, and we want to look for the string access denied. So search for strings. Why is there no string? Maybe it's because I had something highlighted. Search for strings. There we go. We want to look for access denied because that's what we see. Go to the cross-reference, which is where this string is used in the program. And we can see we got access denied, access granted. And if you want, we can probably easier to look at the call graph if you're not used to looking at assembly. So this is the access denied. This is looking like access granted. And up here, we're doing enter access password. We're doing a call to gets. Gets is going to get input from the user. And then we're loading the effective address, never fear I is here, into RSI. And then doing a string compare. So we're doing a compare against probably RDI and RSI. RDI will have what we put, and then RSI will have never fear I is here. So easy way to get this is just to probably strings it. And we can also look for N3. There we go. Copy the password. And then run the garbage program. Paste it. And we have a few options. And 4 cancels out. So the one thing I want to look at is there any hidden options? Because it didn't really give me any input. So let's go back to Ghidra. And let's see. If we go to main, check user, let's go. Oh, we can cheat and just look at this decompiled output. So we have a few while trues. Let's see. If local 10 is not equal to 2, then break, then we get launch, check balance, and this is going to be 1. 3 is cancel, and 4 is exit. So we only see 4 options, 1, 2, 3, and 4. If we go back to this call graph, it may be more obvious there. So if EAX is 2, if EAX is 1, EAX is 4. So it doesn't look like there's any hidden options here, because we would see like if EAX is equal to 9, A, B, or something high. But we don't see any of that logic here. So I'm going to go with there's no hidden options. So the next thing I do is just put long strings whenever I have input. And we'll try to see if the program crashes. And we get a segmentation fault there. So that is a good sign. Let's copy this password and we can try putting those A's into the next one and seeing if it always crashes on long strings or that was just a random thing. And we don't get a seg fault, it just closes out. So if you look at the code, we can go back into main. We're doing a call to scanf to get user input, I believe here. If we look into the auth function, we have a call to, let's see, where is it? Gets, str copy, and string compare. So these are going to be where the vulnerable functions are. If I had to guess, just looking at this briefly, str copy, this is probably assigning the memory space for str copy. Looking at the decompiled, yep, it is. So local 24 is going to be, wait, why is that saying 12? Oh, yeah. 12 times 16, I guess? Is that what that is? Is that going to be 100? No. Not sure exactly what's going on, but we're assigning character space for the password. It should be 12 bytes in length, and then loading it on. And then we just overload it and start overwriting the stack. So let's just go take a look at this binary. If we go back to my box, we can do gdb./garbage, and this is just regular GDB. In previous videos, I had used PEDA, PEDA, Python Enhanced GDB. I'm switching over to Jeff, which is GEF, and mainly because Jeff is maintained and PEDA is not. So let's go and install this. The first thing I want to make sure is installed is CMake. If I don't do this, then when installing some other dependencies later, it will error out with some odd errors. So make sure I have CMake. And then we can go to GEF, GitHub. And why do they pronounce it Jeff but call it Gef? I have no idea. I can only assume it's to try to get people to pronounce GIFs correctly by putting a G and saying it's a J. But let's just go down. We can install it either two ways. We can run this wget script, or we can do it manually. I'm going to do manually because I hate piping sh into wget, even though I'm not going to analyze this code, so really there's no point not to, other than, I guess, I don't know. So now when I run GDB, we get 4 commands cannot be loaded. If we type Jeff missing, we can see it tells us to install a few things. So I press Control D to exit, and then let's just install these. So we want to install the Keystone engine, and this is the thing that's going to fail oddly if you don't have CMake. Then Unicorn and Ropper. This last one is also Keystone engine. So those 3 are the ones I want. And then while that installs, let's go back, and we want to download pwntools because we'll use this eventually. So go to pwntools. I'm making sure I get the Python 3 version because I like doing everything in Python 3 now. We'll have to do it one day, so might as well learn it now. And then we can, I guess, install this while that's running. So once that's done, then we can do this. I've paused the video for about 5 minutes, so all this stuff would finish. So we can run the final command, which is pwntools, and I forgot we need one last thing, which we'll get an error later. We need the GDB server. So once this is installed, we have everything we need. And the exploit's going to be very similar to the one we show in Bitterman, so if what I say doesn't make sense here, go watch that video because I'm going to try to explain it in 2 different ways. So there we go. It's going to be a classic ROP chain with a memory leak. So if we look at the garbage binary, crap, I forget the password. Where is it? Can I not get this? And 3, there we go. If we look at this, we have a few things, and the program itself has calls to print or puts something to print output. So what we're going to do is inject in one of these calls using a ROP chain. So it's return object oriented programming, I think, or return-oriented programming, something programming. Essentially, think of it like a deserialization exploit. We can't inject any new code, but we can hijack any calls and replace the arguments. So what we're going to do is hijack this call to puts or print and have it print us a memory address that's within a linked library, which is going to be glibc. That's going to allow us to calculate the offsets of exactly where libc is loaded, and then access other calls that aren't exactly used in this program but are available to it because of libc. The call we'll probably use is system, so we'll just say, hey, leak the input of this put statement, get the location of system. I'm explaining it horribly. Let's just do it and explain it slowly. So the exploit is essentially going to do something like this. Let's just call this poc.c. Include stdio.h int main. So we're going to say a can be 12 characters, and then we want to load a memory register into A. So, whoa, I don't know what just happened there. P and puts. So this is going to load the address of puts into the variable A, and then we can do puts A. So super simple program. If we gcc, man, my keyboard is going wacko. It just closed that whole pane. Okay, gcc poc.c -o poc. We can see the memory address of puts is changing every time we execute this program. And that's just because of ASLR. But we know that system is going to be a set amount away from this, because libc isn't randomizing the addresses within itself. So if we have libc here, we may have system, puts, setuid, etc. And these are always in the same location. Libc may be loaded at memory address 100, which makes system 0x101, and then puts would be 0x102, setuid 0x103, and everything else will say 104. So what this exploit is doing is saying, hey, we know puts is 102, so if we subtract 1, we'll know exactly where system is. And that information is important to us because we don't know where libc is loaded. This could be, instead of in 100, it could be 45, which makes all these 45. And this is essentially why that memory leak is important to us, because we need to know where libc is loaded. Once we leak the location of one address, we can put together where everything else is. So that's essentially the exploit. So the very first thing to do is find out exactly where this memory cache is. So we just did a bunch of A's last time. We'll do this again. So we'll print 300 A's, copy this to the clipboard, and then we'll do gdb./garbage, R for run, enter the password, and crash the program. We see it ended on a return, which is going to bring us to where RSP, the stack point, is going to be pointing. It's just pointed to a bunch of A's. If we look at RSP up here, it's pointed to this memory address, which is just saying, hey, it's a bunch of A's. And then that's why the program's crashing, because it can't return to this address. So what we have to do is find a way to put a memory address here. So we're going to do pattern create 300, and this is going to create a never repeating string. So if it crashes right here, we can know exactly where this is. So it'll make more sense once we do it. So copy that, run to run it again, paste it, and we can see RSP is pointed to right here. So if we do a pattern offset, or I think it's pattern search. Nope, pattern offset. If you're ever confused, you can just type help pattern and see what it is. Pattern offset's an alias for pattern search because pattern offset is what PEDA uses. So, and that's the cyclic pattern. That's what it's called. But we see it's found at offset 136 from a big endian search. So if we do a Python command again, so python-c print a times 136, and then we can add b times 8, and then c times, oh, we don't even need c. We can just do b times 8. And then paste this, run this again, paste it. We see we still crash, but RSP is pointed to B's. And we confirm by looking at the register, this is pointed to B's. So what we have to do now is induce that memory leak. In order to do the memory leak, we need to have the program call something. So we're going to look for a function with ropper, so ropper -- search, and we want pop or question mark I. Okay, it's got to be in quotes. So pop RDI and return. The reason why we want this pop is because in 64-bit languages, when you do syscalls, or not syscalls, but arguments are stored in registers. In 32-bit programming, you just put everything on the stack, and then when you called things, it would just pop it off the stack to get arguments. In 64-bit, it's a little bit different. It pops things out of registers. The order it generally does it is RDI, then RSI, RDX, RCX, R8, R9, are the registers it normally uses for arguments. So with this pop RDI, we're going to say, hey, take this first value off the stack and throw it in RDI, and then return. And return is going to be the address of RSP, which is going to be the function we want. So that function goes, looks at RDI, says, okay, this is the argument we want to run with, and then execute. So if we went back and looked at our super simple test binary, I think I called it POC. If we do GDB POC, run, break main, run. Let's see, can we easily see this? So where is this? Yeah. So we're loading the address. Right here is going to be the output of this sprint command. So we're loading that into RAX. RAX is normally stored for like the output. And then saying, hey, RAX, go into RDI, and then do this puts command, which is going to print what is in RDI. So that was a super simple POC.c file we did before. Always helps when going through and learning assembly to have some source code, compile it, and look at what it does. So we can begin creating our skeleton exploit. V exploit.py, and we can say pop RDI is equal to this address. And while we're at it, we should just create the whole skeleton for our exploit. So we'll do from pwn import star, and we want to say context terminal is equal to tmux new window. And what this is going to do is set GDB to always open up in a new window for tmux. Super handy. So p is equal to gdb.debug./garbage, and then break main. Okay. And we also want to set the context to be OS is equal to Linux. Forgot the single quote. and architecture is equal to AMD 64. So whenever we do memory addresses and things, it knows exactly what format it is. So the first thing we need is the junk variable. This is going to be A times 136. And then pop RDI is going to be this address. And then we got to get a few more addresses. So we can put a argument onto the register. What is the argument we want to put on it? We want to put the global offset table's address. So let's do objdump -d garbage and go within this binary. So if we grep it for puts, the global offset is going to be right here. So this is going to be GOT puts is equal to 0x paste, and we want to pack these in 64-bit format, so P64. And let's see, the address of puts, this is going to be the procedural link table, is going to be this. I don't think I explained this yet, but essentially, there's some magic involved with like ASLR, and within itself, the binary knows where the addresses it actually used are, and then it puts a reference to that into the global offset table. And that global offset table has some magical linking to find out where libc is loaded. So it's kind of a trampoline to get to effects. In order to do put, I call put on this address. It knows to go to the global offset table. The global offset table knows to get me to where libc is loaded. So we have this now gadget. So we can say gadget leak is equal to pop RDI plus GOT puts plus PLT puts. And what that's going to do is it's going to pop this into RDI and then return to RSP, which is what PLT puts will be at. So we can do p.send line junk plus gadget leak. So that should be fine. p.interactive. And if we do Python 3 exploit.py, continue, it looks like we crashed. I'm going to do Control D to exit. And let's see, line 13 can only concat strings, not bytes. So was it 13? Junk gadget leak. I probably have to convert this from string into bytes. Standard Python 3 errors. So we can continue here. Okay, we hit a breakpoint, continue. We have now crashed. And we are now crashed inside of main. We're no longer in that auth crash that we saw before. And RSP, let's see what RSP is set to. Some libc address. So let's exit this. And we see it printed something weird. So this is going to be the memory address we leaked. We could run this again. Continue. Exit. And we get something different because remember, it's random. So this is a good start. The best way to view this, I guess, would be, let's see, we can do p.receive until. Do we have something? I guess access denied, and then we want to grab what's after this. So receive until access denied, and then we want to do leaked put is equal to p.receive 8.l. We just do this and we can print leaked put real quick to show you what it is. Python 3, continue, will crash, and this is what we printed. So it's always going to end with a new line, and we don't want that new line. So that's why I'm going to call the strip. So dot strip. So that got rid of that /n, and then we just want to adjust it 8 and then null byte. So this is going to be a formatting thing. So now when we print, we can see it will always be 8 bytes long, and the padding will be null bytes. So that is the memory address. That's what LAdjust did. This just said always be 8, do padding of null byte. So instead of doing print here, let's do this better. We can do log.info f leaked address and then leaked put. Okay. Python 3 cc. Okay, that looks fine. We may want to convert that into hex so it's easier to read. To do that, all we put is .hex like this. It's easier in Python 3 than Python 2, thankfully. So now we have leaked address, this. So, I guess we could change it to little endian format. I think this is in big endian. I always get the two confused, but these zeros should be on this. So this string is reversed, but we'll worry about that later. What we have to do is make the program not crash now. So that's super simple. All we do is go back here and the same object dump command, except we want main. We want to get back into the beginning of the program. So main is going to be 403ff0. So we just grab this, go to exploit, and then we can put plt main is equal to p64 0x, and then we can do gadget leak plus, we'll put it in gadget leak, plt main. And because main doesn't get called with any arguments, we don't need to pop anything into RDI or anything, so we can just leave this, run the program, continue, and we crashed. Why did we crash? That is bizarre. Let's see. PLT main 403ff0. Let's take a look at this again. Garbage main. Where did I get 403 from? Call queue. Oh, that's libc main. My bad. So, what I want is this address. It helps to have things in max window when copying things. So, let's go back to exploit. Go to main, put the address, run the exploit, continue, breakpoint, breakpoint, and right now, if we put anything, it's probably going to say access denied, and then kill us, because we just leaked the address and then continued running the program. And the reason why we continued running the program is because every time we start this program, libc's address is going to change. So as long as we don't crash the program and go back to main, we'll be fine. If we went back and did, let's see, we could probably bypass this password prompt. So if we go out of auth, where's main? Come on, main, where are you? Function graph, let's see. Set username, call auth. Let's see. Let's just try putting 40164A. See what happens. I have no idea what's going to happen here. Let's do plt fun is equal to p64.0x40164A. Okay. So instead of main, let's do fun. Run the exploit. Continue a few times. We sec faulted. Okay, let's just do it. Continue going through how we were. Get rid of fun. We can't have fun. Let's just do main. So now we're back at the beginning. What we have to do is figure out where libc is now, because we've leaked the address of where puts is within libc and then continued running the program. So what we're going to do is Readelf on our libc program. So libc is in, I think, user lib x86. Is this it? And then readelf-s libc, yep, .so.6. And if you don't know where libc is, you could probably do LDD, which is going to show all the linked libraries on the program, and that will point you exactly where libc is. So, could be handy. So we want to grab puts, and puts is going to be right here, 74040. So we can go back in exploit. Actually, I already have exploit running. Okay. So libc's address, we can put it right here. Puts underscore libc is equal to p64 0x740. Let me just double check that one. Readelf puts. Okay, that should be fine. The next thing we need is system, because we're going to want to call system. So that one's going to be at 46FF0. So copy this. System. Actually, let's do libc underscore puts. And then libc underscore system is equal to p64 0x46ff0. And let's see, we probably should have SetUID as well, because if this binary doesn't make a call to SetUID, we'll have to do that. So we can grep for SetUID. This is going to be C8910. So SetUID libc SetUID is equal to p64 0x C8910. And then the last thing we need is a argument to put within the system, because if we just call system like this, it's going to crash. We need to give system an argument. So to do that, instead of doing readelf, I'm going to do strings -a for all -tx is going to show us the memory location in hex where this is located, or not memory, the size in hex. And then grep for bin sh. And we need to specify libc.so.6. And we see bin sh is loaded at 183 CEE. So we can say sh libc sh is equal to p640x183cee, and that is going to be all the variables we need for the exploit. So what we should do is go back and label where we got these. This was ropper, this is objdump, this is objdump, plt main, objdump, this is Readelf, because there's a few ways to get these, and sometimes they give different values. So it's always nice to know exactly how you got all your functions. Anyways, we can get back into the coding, and we have the leaked address, so let's calculate the offset. So the offset is going to equal the unpacked version of leaked put, and then that's going to be the difference of the unpacked version of libc underscore puts. And we can say log.info f offset is equal to offset. So now we know where libc is, at least libc puts is, so we can do the difference of all the other functions we want. So let's do system location is equal to unpacked version of libc underscore system plus the offset, and then we will want to do SetUID location, the same exact thing, but SetUID, and then we'll need the string location for sh, and this is going to be again the same thing but sh. And we can do log.info f system underscore location, and we'll do UID. This is SetUID location, sh location. We'll just do it this way in lowercase. Okay, and we probably need to put these in hex. Okay, if we do Python 3 exploit.py, continue, int has no value hex. Let's see. We can convert these to bytes, and we'll do byte order is equal to little. I'm sure pwntools has a function for this, but it should be fine. Convert negative unsigned int to unsigned. Something failed marvelously. That time it didn't crash. So now we have the offsets for everything. The byte order is flipped, which isn't ideal, but let's see. For this, we're going to want little endian, but for our ability to check, I'm going to change this to big real quick. And you'll see what this does. So continued. We can close this session. So these are the addresses we're used to seeing, so we can test everything. So let's go back into GDB, Control-C to get and break, examine this address, And we can see that is the call to libc system. We can examine this SetUID address. There's the call to SetUID. And then let's do bin sh. And we're going to see this isn't going to look right. But if we say, hey, don't examine the hex, examine it as string, we can see that's bin sh. So we know we have everything good. So let's convert these back into little. And then create our gadget chain. So we need, this will be gadget to leak, and this will be gadget to code exec. So the very first thing we do is call, create the variable. So gadget RCE is equal to pop RDI plus, this is going to be the SetUID call. So we're going to do p64 0 because we want to put 0 into RDI. And then SetUID location. Or not that. Is that what I called it? Yeah. SetUID location. So what this is going to do, it's going to pop RDI, put 0 into RDI, and then call SetUID. And SetUID is going to see, hey, RDI has 0, let's do a SetUID 0. So the next thing, gadget RCE is equal to pop RDI, and then we got to put the location of SH, and then we put the system location. Okay. And then p.sendLine is equal to junk plus gadget RCE. And then we'll get interactive. So run this exploit, continue. Segfault. Let's go C, C, C. For some reason, if I go too quick, it looks like it's crashing. But inside of this now, I have my shell. So everything looks like it is working just fine. The final thing we have to do is make our exploit go through SSH. So let's get rid of context terminal and this debug thing. And what we want to do is S is equal to SSH host 10.10.10.139. User is equal to Margo, and her password is equal to something. Let's go here. It's going to be I am God $08. I bet a previous password was I am God $07. But paste that. So that's going to SSH in, and then P is equal to SSH.process user bin garbage. So let's see if this all works. Python 3 exploit.py. It's SSHing in. Should give us all the leaked information soon. There we go. ls, and we crashed. And the reason probably is all our libc addresses are probably going to be wrong because it's a different version of libc. So let's go back into SSH as Margo, and we can just do LDD user bin garbage to find the location of libc. And then if we go back to our exploit, everything we got from libc was here. So maybe we could do objdump garbage, 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 libc, 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 libc. So Readelf on libc. Let's just do readelf-s libc.so.6. Okay. grep-I puts and system and SetUID. Okay, these are the ones we want. It's going to copy this, and then we'll put them in. Set paste. Okay. So let's see. libc put is going to be this one. Did I not do that correctly? That's put. Yank word. P. There we go. And we can get rid of these arrows. Okay, libc system. So system is right here. Yank word. Put. Delete this. SetUID. Where are you? SetUID. YW to yank. P. So now we put the new location for put, system, and SetUID. We just need libsh, and that was gotten through strings. So go back to Margo, strings -a for all, tx, libc so6, grep, bin sh, and that's at 1b3e9a. So paste, and now we've updated our locations. If you go to the Bitterman video, there'll be ways to have pwntools be able to do this automatically. Leaked address was all zeros, so it failed. Let's try this again. Leaked address all zeros. There we go. ls user.text. Who am I? Root. cd/root. wc-z root.text, and you can read it. But as I was saying, Bitterman has ways where you can just say, hey, pwntools, go read libc at this location, and then dump all the offsets. So definitely check out the Bitterman if you want to do some more advanced things. But that will be the video. Actually, we can go over the exploit script real quick, in case you have any confusion. So right here, importing pwntools. Here we are telling pwntools to execute SSH and garbage. This gets us to the RSP overwrite. This will put value into RDI. Actually, I don't like the way I word that. Let's do take top value off stack, put into RDI, because that's exactly what pop does. Global offset pointer to libc puts location. This will be the location of calls in PLT, which is the procedural linkage table, I think. And then this is location of stuff in libc. Calculate offset to get real location, or we'll get loaded location would be a better way to put that. Okay, this is going to gadget to leak, put GOT puts into RDI, call puts to print GOT puts, then call main to not crash. Okay, this is going to be getting the memory address. This piece was calculating offset. Then this is going to be using offset to find loaded addresses. And then this is going to be printing output for debug. Probably should have put this under like log.debug, but oh well. Gadget to code exec. So this is going to be put 0, which is the UID for root, into RDI, call SetUID. And then this gadget is going to put bin sh into RDI, call system. And then have shell. And that'll be it. So hopefully going through the program helped you a little bit, but that'll be the video. Take care, and I will see you all next week.